Hey, what's going on, guys? So you're back really quickly. Well, I just finished recording the last lecture, and I was kind of in the middle of a section, just starting going into parametric equations, and it was like, do I really want to put this off? So I was like, nah, I'll just record another lecture right now. So let's actually just jump back into it, because what else am I going to do? Okay. None of us have anywhere to be because we're all being responsible citizens and maintaining our social distance. So let's actually jump right back into it. So here we go. Last time we introduced the notion of parametric curves. Last time for me being like 10 minutes ago. For you guys, I don't know, maybe you watched this the next day. Yeah, we introduced the idea of a parametric curve. Basically what this is the following. So we have variables that we're used to dealing with, x and y, for example. Let's just, for our purposes, for calculus, we have the x and y variable. X is usually thought of as the independent variable, the guy that we put on the horizontal axis in the Cartesian plane. Y is the dependent variable that we write on the vertical axis in the Cartesian plane. But every now and then we want to represent each of our variables in terms of some other variable. We want to think of each of our variables as being functions in their own right, that they don't really depend on each other necessarily, or we don't want to think of them as depending on each other, but we want to think of them as depending on some other variable. This other variable we call a parameter. And once we describe our variables x as a function, x of t, of this new parameter, and y is a function y of t, we say we've formed parametric equations. Once we take two parametric equations together, we call that a parametric curve, because pretty much what we can do is we can figure out what the x coordinates are doing or what the y coordinates are doing. We can put those guys together and figure out, well, we know that the x and y coordinates have to behave like this together, and we can end up tracing out a curve like that. So that's what we did last time. We did a couple of examples of that. We also noticed one useful fact. Oh, I thought a sneeze was coming, but it left. We also noticed a useful fact that one added benefit of parametric curves was there was an implied direction that was associated with them. So not only can I talk about a parametric curve, which can be something familiar to me, like a straight line or a parabola, but I can think of us as moving along that curve in a certain direction. So that was pretty cool. We didn't really get much farther than that. So we are just going to continue. So this is where we stopped off last time, which for me was just actually a few minutes ago. Where are we? Okay, let's leave that up there. Let's go. Okay, so now what I want to talk about is, boom. So I mentioned that going from a situation where you have a scalar equation to a parametric set of equations to a parametric curve, we call that a parametrization. And so now what I want to talk about is circles. I want to talk about the standard parametrization for circles. So let's say you have a circle, x minus h squared plus y minus k squared equals r squared. Now remember what this guy is. This is a circle with radius r and center h comma k. Okay, so you have basically this circle. There's a center coordinate here, h comma k, and the radius is r. Okay. How can we come up with a parametrized version of that circle? Well, there's a standard way to parametrize it, and it is what I mentioned here. And this is just something which I would recommend from now on that you just memorize. This is one of the nicest, neatest, most straightforward ways to actually parametrize a circle. Let x equals r cosine theta plus h, y equals r sine theta plus k, let theta run between 0 and 2 pi, or anything that covers 2 pi, and you would actually trace out a full circle. It's worth mentioning here that the R value here is the radius of the circle. It's just taken to be some magnitude, something greater than 0. If I were to put different values on the x and y, so let's say x was a cosine theta and y was b sine theta, a and b were not the same, they were just positive numbers. What you would get is you would have an ellipse, like the radius in one direction would be longer than the radius in another direction, and you'd end up getting a kind of stretched out circle. But as for a circle, as we're used to thinking about it, this is a standard parametrization. You might think about, why is this a parametrization? Well, if your x is equal to r cosine theta and your y is equal to r sine theta, let's say this is plus h, this is plus k, what you could actually do is you could actually solve for the cosine here. That would be x minus h over r, and your sine would be y minus k over r. And so since we know that cosine squared theta plus sine squared theta equals 1, we can obtain x minus h over r squared plus y minus k over r squared equals 1. And so that would actually give us x minus h all squared plus y minus k all squared equals r squared, if I just multiply both sides by r squared. So by connecting this by using the Pythagorean identity for sine and cosine, I can directly connect this equation to a known identity that must work out. And so this just gives me another way of expressing this equation. So this would be the scalar form of a circle. And of course, it's only a circle in R2. We'll talk about that in a few more lectures. And I can, then this here would be the parametric form for a circle. Okay. Yeah. Just don't like it. Okay. So by just taking advantage of this trig identity, I'm able to realize that this equation fits very nicely with sine and cosine, which again, from trigonometry, we kind of have that idea already, that the x and y, we can kind of associate them with cosine and sine respectively. So that gives a very nice, straightforward parametrization of a circle. Now, of course, there's a special case here, which we'll talk about more in future lectures, is circle with center of the origin. Of course, we can just think of that as x equals r cosine theta, and think of the y as r sine theta. And that would be a set of parametric equations that would describe a circle of radius r centered at the origin. So that might be a special case that we want to look out for. Now, as I mentioned in the last lecture, parametrizations aren't unique. There are actually many ways to parametrize a curve. There are many ways to actually parametrize a circle. We'll actually talk about one in the future as well. But for now, this is the standard way to parametrize a circle. That's one of the important things that you're going to want to have memorized, so I'll just mention it there. What I want to talk about now is moving on to the calculus of parametric curves. So we know what parametric curves are. It's when we want to express our x and y coordinates, or whatever set of variables we start working out with. We want to express them in terms of other variables. We want to think of them as being functions in their own right. Now, it stands to reason, if I'm given a curve in parametric form, now I know there are times when I'd be able to convert that to a scalar form and figure things out. But for obvious reasons, notice that I have to be able to solve equations to do that, and that in and of itself presents a challenge. Not all equations are easily solvable in that sense. So it may or may not be very efficient for us time-wise and computation-wise to actually go to the scalar form all the time. So that being said, we're in a calculus class. We want to be able to do calculus with our curves. So now we have to figure out a way, well, given a parametric curve, how do we go about doing calculus with this curve? How do we take limits? I'm not going to talk about limits in this at this point. Am I going to talk about it at all? That's really something you'll go into in multi 1, but we are going to talk about derivatives. How do you take derivatives of this curve? I'm not going to talk about integrals. You will deal with that in multi 1. But I do want to touch on derivatives. So we know that we're calculus students. We've been in Calc 1. We realize that derivatives are important. They help us talk about rates of change, how fast something is moving, has all sorts of applications. So it stands to reason, if I have this new way of looking at a curve, is there a new way of looking at the derivative? How do I go about doing calculus in this scenario? And the thing is, it's actually not that bad. It's really just an application of the chain rule, right? The chain rule. Now, this is one way we can think of the chain rule. So dy dx equals dy du times du dx, right? Now, here, u is the inside function. So it's like, suppose we have, I don't know why I put a colon there. Say some function y, and there's an inside function u, and we wanted to find the derivative. Well, how did we go about doing that? Well, we took the derivative of the outer function, left the inner function alone, then we multiplied by the derivative of the inner function. Now, this is a form that most of you are probably used to seeing the chain rule as written in, but we can actually express this as the derivative of y with respect to u. It's just the derivative of y where the inner variable plugged in is u. And then the u prime here is just the derivative of u with respect to x, right? And so that is just another way of writing dy dx, the derivative, when we have an inner function u. So this was one way. Normally it's mentioned in Calc 1, although we don't do anything with this version, but it's equivalent to the version you would have seen in Calc 1, which would be something like this. The derivative of f of g of x is f prime of g of x times g prime of x. This is equivalent kind of by that kind of manipulation. And that's what we're going to use here. So what we're going to do when we want to talk about the derivative dy dx, the other variable that we're interested in is t. What we can think of is, think of the t as the inner function. And so we can say that the dy dx is really dy dt times dt dx by the chain rule. And so I can actually rewrite this a little bit to get that dy dx would be equal to, well, dy dt. And then if I take this, that should be dt dx. And if I just think of this dt dx as a fraction, flip and bring it in the denominator, that gives us a formula by which we can calculate the derivative. And when it comes to parametric equations, that's how we're going to think of the derivative. take the derivative of the y function with respect to the parameter t, then take the derivative of the x function with respect to the parameter t, divide them, dy dt divided by dx dt, and that will actually give you dy dx, and this is the slope. Of the parametric curve given by x equals x of t and y equals y of t. Meaning, if we were to find a way to represent this as a scalar function, we could go from these two equations to a scalar function, then this function here will actually give you all the same outputs that the dy dx in the traditional sense would actually give you. And so using the Leibniz notation is very easy to actually talk about the derivative in this new context. It's actually surprisingly easy. In fact, the second derivative, it's going to seem like cheating, but we can actually find that in a very similar way. Basically, using the Leibniz notation, just know that the second derivative is just the, I'm still in green. We can think of the second derivative as the derivative of the first derivative. In other words, I can think of that as this guy over dx, right? And that really shouldn't be weird that I wrote it like that. So this reminds you of, hopefully it reminds you of, if I were to take d dx of some function y, another way to write that is dy dx, right? So I could say d dx of x squared. We understand that really you can write it as dx squared dx. We don't really do that very often, but it's the same kind of manipulation as this kind of dy dx. So I just move this guy to the top, put it beside the d. And so what we do now is I am going to multiply and divide by 1 over dt. So the approximation of a small change in dt is what I'm going to multiply by. And so this now, I can just move that in. This is d dt of dy dx over, well, dx dt. And that is your second derivative. D squared y dx squared is that guy. Okay. So this is how I can find the first and second derivative of parametric equations, parametric curves. So using the chain rule and Leibniz notation, we could derive all these formulas. And yeah, that's it. So these are just things that you know now. These are just new formulas for you to know. Now, there are some things that we often like to know when we talk about the first derivative, and that is how we know that, hopefully by now we know that it means the slope of a tangent line. But sometimes we want to find where a tangent line is horizontal. It's also sometimes important to find where a tangent line is undefined, and so on. And so this is kind of something that we're often interested in. And just a note on the horizontal and vertical tangent lines, when it comes to parametric curves, these features are very important for us. Realizing that the first derivative is a fraction. If the derivative is 0, which is how we would get a horizontal tangent line, what that would mean is that this fraction needs to be 0. Now, a fraction is only 0 if the numerator is 0, right? So assuming that the dy dt is 0 and the dx dt is not 0 at the same time, because you don't want to divide by 0, you would get a horizontal tangent line. So that's just a fact that we can easily extrapolate here. Now, of course, if your dx dt is not 0 and your dy dt, if your dx dt is 0, meaning the denominator of this fraction is 0, then of course that means your slope is undefined. As long as the numerator is not 0 at the same time, you get a vertical tangent line because you get an undefined slope. There is a special case, of course, if both are 0 at the same time. This gives you a 0 over 0, which, as you might recall from Calc 1 and earlier in Calc 2, where I mentioned it a few times, is this is an indeterminate form. So you'd use something like L'Hopital's rule or something like that to help you figure out what the slope would move to in those situations. But these guys should actually follow directly just from looking at the definition of the first derivative. So hopefully that is all well and good. That being said, nothing else to talk about the derivatives here, just going through some more basic calculations, the kinds of things that we would do in Calc 1, but I want us to do it now with parametric curves. So suppose I have this curve right here. By the way, just for fun, here's the graph. Now, you should start to appreciate here that this will actually be very annoying to get it in scalar form. So you wouldn't want to convert this to scalar form and then go through and do all these problems like finding a derivative, find the second derivative, find where the tangent line is horizontal and vertical, find where the tangent line has slope 3, etc. You might think, well, I don't really like this parametric equations thing, which give it time. You will begin to love these, and because they're very, very useful and very convenient. But if you wanted to transform this to the scalar version and try to do the first derivative the way that you've always done it, you're going to run into a hiccup. So first of all, solving for t in this situation is going to be really messy because you'd have to use like the quadratic formula or something. Then you're going to plug that into this cube. It's not going to be a fun time. Now, just to kind of show you how much not fun that would be, let me just copy this down on a piece of paper so that when I move to the... Okay, so we're looking at x equals t squared minus t plus 2, and y equals t cubed minus 3t. Okay, so let's actually just graph this for fun. I wouldn't ask you to graph this, but just for you to just see what kind of curve we're looking at here. Let me share another screen with you. Okay, so this is an app called Graph. I really like it. And let's put on a grid here. Not that it's necessary, but whatever. So here's a function. Let's actually insert a function. I want a parametric function, and the x is t squared minus t plus 2. The y is t cubed minus 3t. From minus 10 to 10, I think that's fine. Okay, so there is what the curve looks like. Now, as you can see, it does not pass the vertical line test. It is not a function in the way that we normally think about functions. So, yeah. But I just want you guys to see the creature that we're looking at here. Let me kind of, how do I move this to... Okay, there we go. And let's move this back to OneNote. Okay. So there's the picture. Just for fun, I guess. Like I wouldn't ask you to graph that, but that could give you some idea. It's not even a function, which means if you tried to solve for this to look like y equals f of x, can't be done. You couldn't do it. You couldn't do it even if you want to. But as a parametric curve, individually, the x and y are very well understood. These are very nice polynomials. Again, hopefully you're kind of seeing ways in which parametric curves can be useful. A very complicated curve in scalar form, it's not even a function in scalar form, but in parametric form, the x and y coordinates don't actually behave too complicatedly. This is an English class, let's forget about it. Okay, so let's go through and do all this good stuff. Find the first derivative, find the second derivative, find the points where the tangent line is horizontal and vertical, where the slope is 3, find what is the equation of the tangent line when t equals -2. So let's actually figure this out for this crazy looking graph over here. So dy dx. Well, this, remember, is just dy dt over dx dt. Now our y is t cubed minus 3t. So I'm just going to take the derivative of that. 3t squared minus 3 over the x is t squared minus t plus 2. So the derivative is 2t minus 1. And that is our first derivative. So again, a very complicated curve in terms of x and y. However, at any given time, give me a t value, and I can actually tell you what the derivative is at that value. And of course, if you give me a t value, I can find an x and y coordinate, so I can tell you at what x and y coordinate, what is the slope. Okay, so for example, if I wanted to find what is the slope at notice that 2, 0 is on the curve. This, of course, means that your t is 0, and so your dy dx would actually be +3. Huh? Pretty nice. So I can find the slope given some coordinate, and yeah, that's nice. So I didn't even have to convert to a scalar equation to actually figure that out. So yeah, pretty neat. Then next, B. Let's find the second derivative. So remember the second derivative, that's just the derivative with respect to t of the first derivative over the derivative of x with respect to t. And remember where our x is equal to t squared minus t plus 2, and our y is equal to t cubed minus 3t. And so this would be the derivative with respect to t of, well, we had the first derivative up there, 3t squared minus 3 over 2t minus 1 over the derivative of x with respect to t, 2t minus 1. And now we can just actually calculate this. So in the top, I'd find the derivative. This is all calc 1. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared But of course, I divide again by the 2t minus 1, so that becomes cubed. And of course, now I can multiply this out. So this here would be 12t squared minus 6t. This would be minus 6t squared plus 6, looks like. And so the derivative here is going to be 6t squared minus 6t plus 6 over 2t minus 1 cubed. And that, ladies and gentlemen, is our second derivative. Pretty good. So our first derivative and our second derivative, just straight up using these formulas. Again, Calc 1, like I said, way back here, we're keeping it basic. So we're just, we're looking at the world in a new way using parametric curves. Just want us to go back to basics, kind of figure out how we'd go about sketching them, how we talk about derivatives, and that's how we talk about derivatives via these two formulas. Let's move on to the next problem. Find where the tangent line is horizontal and vertical. So let's copy this. Let's copy this one. Is that part C? Now remember, for horizontal tangent line, let's do the horizontal first. C part 1. So remember, we need dy dt equals 0, dx dt not equals 0 at the same time. So this means our dy dt, this means 3t squared minus 3 must be equal to 0. Of course, that means t equals plus or minus 1. And you will just make a note here. Note dx dt, which is equal to 2t minus 1, is not equal to 0 for t equals plus or minus 1. So these guys are actually the guys that we want. Now, it did ask you find the points. So I do need to talk about coordinates here. So this just means when t equals 1, our x would be equal to 1 squared minus 1 plus 2. That's just 2. And our y would equal to 1 cubed minus 3 times 1, which is minus 2. So that gives us 2 comma minus 2. When our t equals minus 1, our x would be minus 1 squared minus a minus 1 plus 2. So of course that's positive 1 plus 1, so that would be 4. This is going to be a minus 1 plus 3. That's 2. That gives you the point 4 comma 2. So these are the points where we have a horizontal tangent line. So that's it. Moving on to the vertical scenario. Oh, this is something that we're going to do later. Arc length, pretty cool stuff. And that's just also something for you guys who are missing integrals, because that's going to be an application of integrals. Yeah, let's talk about vertical tangent lines. So we hit a vertical tangent line when our dx dt equals 0, and hopefully our dy dt is not 0 at the same time. Now remember, any scenario where both your dx dt and your dy dt equals 0, this is an indeterminate form. You're going to want to approach those t values with limits and use something like L'Hopital's rule, or maybe even a series to actually figure these things out. But here, we need dx dt equals 0 and dy dt not equal 0. So this means 2t minus 1 equals 0. This means that t equals a half. And of course, just note dy dt is not equal to 0 for this t value. So we're good. T equals a half is the only point we actually care about. So now when t equals a half, our x is going to be equal to, what was our x? Okay, so our x is going to be, I'm going to plug in a half here. It's going to be a quarter minus a half plus 2. Okay, so that's going to be minus a quarter plus 2. It's 2 minus a quarter. Or let's just think of this as minus a quarter plus 2 is 8 over 4. So this is 7 over 4. And our y would be a half cubed minus 3 times a half. So this is 1 over 8 minus 3 over 2, or 1 over 8 minus 12 over 4 over 8. Staring at screens. I don't like staring at screens. It hurts my eyes, gives me headaches. If I stare at a screen too long, then I just like then you have to give me arithmetic on top of it. Oh God. All right. So I multiply this by 4 over 4 to actually make the denominator the same. That gives us this, gives me minus 11 over 8. No, hopefully that's fine. And so this means at xy equals 7 over 4, 11 over 8. That's the point for the vertical tangent line. There we go. Hopefully that wasn't too bad. What else do we want to do here? When is the slope 3? Let's copy this here. Ooh, hold on. Okay, we're running running into some conflicts here. I'm gonna need more space eventually, but let's actually continue here. This is something that we'll do even later still. So I'm gonna need more cleanup here, but we'll fix that when we get to it. There's my curve. Okay, I did the cleanup. Let's go with the next problem. So here was the guy. When is the slope 3? Now remember, slope is a synonym for derivative. This means we want to know when is dy dx equals to 3. Now, when kind of tells me that I'm looking for the t value, not necessarily the where, which would be the coordinate. So that being said, let's actually get to that. Now, remember that our dy dx is going to be just dy dt, which is 3t squared minus 3. We actually derived this before, over 2t minus 1 over dx dt. So dy dt over dx dt, that's our derivative. We want to know when that's equal to 3. So that's going to be 3t squared minus 3 equals 6t minus 3. Subtract 3 from both sides. It says 3t squared equals 6t. Okay, pause the video, solve that for t really quickly. Go. Now, if your idea was to divide both sides by t, that is incorrect. Hopefully what you did was move the Hopefully what I did was move everyone to one side, factor out the common term. And so you would get two solutions, t equals 0 or t equals 2. That's when your slope will be 3. Now, of course, you could plug in that 0 and that 2 into the x and y to find the coordinates where your slope would be 3, if you so choose. That wasn't a part of the question though. And the last thing here is find the tangent line when t equals 2. So of course, for a tangent line, we need the slope and a point, right? That's what we need for a tangent line. So reviewing Calc 1 here. Now to find the slope, That's your dy dx. So we want the dy dx when t equals -2. This means we're looking for 3t squared minus 3 over 2t minus 1 when our t equals -2. This is 3 times -2 squared minus 3 over 2 times -2 minus 1. That is 12 minus 3 on top, and this is -5 on the bottom. And so this is -9 over 5. That's our slope. Now, what is the point? Now, when t equals -2, our x would be equal to -2 squared minus a -2 plus 2. That is going to be 4 plus 2 plus 2, 8. Our y would be -2 cubed minus 3 times -2. That's -8 plus 6. So this means the point is 8 comma -2. And so we have a slope and a point. We can find the tangent line. Y minus y1 equals m x minus x1. That's our tangent line. Ta-da! So parametric curves, pretty neat stuff. It's when we want to solve for x and y in terms of some other independent variable called a parameter. Here we're using t. Your dy dx is going to be dy dt. Your dy dt divided by dx dt, that's just an application of a chain rule. That's your second derivative. Now to recap, we can go through and find derivatives using those two formulas. So your first derivative is that. We have this here. And again, I'll share the notes with you. Hopefully you were following along while I was going through this. Your second derivative using that formula, I can figure that out. Horizontal tangent lines is when the first derivative is 0. So this scenario is what we'd want, and I can solve for the t. I can find coordinates if I want. Vertical tangent line occurs when the denominator of that is 0, which you can't divide by 0. You get a undefined slope, but we can solve for that happening. We can find when the derivative is a certain value. We can find the equation of the tangent lines at certain points. We can do all that cool stuff with parametric curves as well, and it's not that bad. Here's something else that will be of interest. There's an idea of arc length, or this is just the length of a curve between some point. So let's actually talk about that. And need some more hydration here. Okay. How do you measure the length of a parametric curve, right? And the answer is in pieces. What do I mean? Well, let's say you have a parametric curve and you care about, okay, so here's one point. This is your initial point, x of a, comma, y of a, right? So this is the curve, x equals x of t, y equals y of t, and my t is going from a to b, right? So the final point is over here, x evaluated at b and y evaluated at b, right? What if I wanted to measure the distance that I would have traveled along this curve to go from this point to that point? That is the idea. How do you go about that? Well, we'll take the calculus point of view. We're going to approximate with something that we do know the length of, and then we just make these little pieces smaller and smaller and smaller, and then just add up all their lengths. And the idea is as they go off to infinity, we would get the exact length. This is kind of the Riemann sums approach to finding lengths. So basically what we do is, yeah, we approximate. Are we having issues here? Okay. So we seem to be having some technical issues. I can't actually choose. What is going on? This thing just started misbehaving out of nowhere. Why is it stuck on that thing? Okay. I have no idea what's going on here. Let me stop sharing and then reshare. See if that helps. Okay, so I don't know what happened there, but here's the thing. Okay, so take a few straight lines, right? So I'm going to approximate this curve with a bunch of straight lines. Okay, so let's say I call this x sub 0, y sub 0. That's the first coordinate. This is x sub 1, y sub 1. That is x sub 2, y sub 2, etc. Right? So I can do this for a bunch. And the idea is the more of these lines I use, the better the approximation to the curve. And the idea is if I use an infinite number of x, y points to make the ends of the line segments, I get to the actual curve. And so I can get the actual length of the curve. And so what I can do is talk about the length of each segment. Length of each line segment. Say the length of the ith line segment. Now, this is, of course, is just going to be the square root of the x's, the x coordinates. So this is xi minus 1 squared and yi minus 1 squared, all square rooted. Okay. Now, one way you can think about this, let's move this out of the way here. I might need that much space. No, I think I put too much space. Now, one way we can think about this is as this is just a change in x. This guy here is just a change in y, right? for the ith location. And what we can do is we can actually multiply and divide by delta t over delta t for the ith location. And so that is the change in t values that goes from this point to that point. That's what I'm using here. And I can actually move one of these guys in there. So I'll take the denominator and I'll move it under the radical, which means I'm going to actually need to square it to move it under the radical. And out here, I have my delta ti. I can think of that. And so now what you do is let I approach infinity and take the Riemann sum. So I'm doing a lot of hand waving here. You don't really need to know this derivation, but I just want you to have an idea of where it's coming from. And what that obtain is L, which we will talk about as the exact length of the curve. And this is pretty much going to be, well, your delta x over delta t, that's just your dx dt, isn't it? Your delta y over delta t, that's your dy dt. Then we have this square root. But we just added up a bunch of lengths. We added up an infinite number of things of this form. We can do that with an integral. And of course, the delta t out here is going to become your dt. So we have this formula. So this is called the arc length formula. And what this does is it gives the length of x equals x of t, y equals y of t for t between a and b. Right? So that's a nice formula. So like I said, very hand-wavingly, so the hand-waving derivation. Some people like to jump from this step to this step. You could actually do it by the mean value theorem. It's one way to think about it. You could realize that your delta x is equal to x prime of t times delta t for some t naught, so that you can take your x prime at some t value and think of it as the delta x over delta t, and you know that's where this comes from. So you don't really need to know that. That's probably a nicer way to do it, but just multiply and divide it by delta t and moving it in. I think it's computationally speaking, you can see why it kind of makes sense to do this. But yeah, that's actually a formula for the arc length. And so what we can do is we can find the length of a curve. So for example, let's find the length of this curve. And let's look at the graph here for fun. Because that curve is pretty complicated. But let us see what the graph would look like. So chair back to that graphing thing. Let's show grid just because function, insert function, we are going to insert not a polar, a parametric function. So x equals the exponential function evaluated at t plus the exponential function minus t. Our y is 5 minus 2t. And I want, where's, I don't know if this gives us the x and y limits or what. But yeah, it looks like a parabola. So I am thinking that this is the t values. So argument range. So we want t goes from 0 to 3. Okay, so that is our curve here. All right, that looks nice. So just so you can see, let me put this in the OneNote document here, copy this function. Okay, so there's our picture. So now this question, now you don't have to know what the picture looks like, of course. But just for fun, I wanted to graph it for you guys. Good luck actually graphing it from that. So we actually want to find out how long is this curve moving from this point to that point. So what we can do is by the above example, we know that the length of the curve is going to be the integral from 0 to 3 of the square root of x prime of t squared plus y prime of t squared dt. So the integral from 0 to 3 of the square root of x prime, that's e to the t minus e to the minus t squared, plus y prime, which is going to be minus 2 squared dt. Now what I want you guys to do, it's been a while since we've done integration, pause the video, actually try that integral, and let me know what you get. Now, hopefully you paused the video and you actually tried it. So this would be the first step. I would just kind of start to expand here. So this will be e to the 2t. This times 2 plus e to the minus 2t plus 4. And we can actually get that guy. All right, now, did you get that far? If not, pause the video. Okay, and try to do it from this point. Now here's the trick with this one. is to kind of notice this pattern. Notice that up here, we had this guy, which is a square. And when we expanded it, we got this guy. So that is just e to the t minus e to the minus t all squared. Now, this guy actually looks very similar to that, as you would notice. The difference is there is just a sign change. So in a similar way, we can think of this guy as that. So what we'll end up with is the square root of, well, it's e to the t plus e to the minus t all squared. And this is going to be for some other time because I'm pretty sure we're out of time for this lecture. And where are we? Okay, so what is that? Well, what that is it's the absolute value. Now in this situation, it doesn't actually make a difference because this is always positive. So it's going to just be it's greater than 0, so the absolute value does nothing, and it just leaves it as that. So what you can do then is you would get integral of that, e to the t, integral of that, it's minus e to the minus t, between 0 and 3. Plug in 3, you get e cubed, minus e to the minus 3. Plug in 0, you get 1 in both, they'll kill each other. That is your answer. That is the length of the curve. So using parametric curves, we can find the length of a curve if it's in parametric equations form. By the way, you could, there's a form for this in scalar form. I'm pretty sure you'll do that in multi-1. Pretty sure. But yeah, we'll end there because I think we're slightly over time at this point. But yeah, this is just us going through the calculus of parametric curves. So I want to stop there. So using these formulas, we can talk about the first and second derivative. We can use these in ways that we've seen before, finding horizontal tangent lines, finding equations of tangent lines, finding where the slope is a certain value. All kind of straightforward. This is something that we have to derive. This is not something that you would have seen before, chances are. But you can find the arc length of a parametric curve using this integral formula right here, which is pretty neat. We can use that to figure out for this parametric curve, which looks like a sideways parabola. If we go from the point where t equals 0 to t equals 3, the length of that curve is going to be this value, which is pretty cool. We'll stop there. We'll wrap up. And I'll talk about this next time before moving into the next topic, which the next topic I want to talk about is polar coordinates, which is going to be pretty cool. At least I think so. Until then, I'll see you guys next time. Stay safe. If you have any questions, you can drop them down in the comment section. Or, yeah, if you're in my class, you know how to reach me through email. So you can do that. I will post the notes to this lecture in the description box as well. So hopefully you guys have been following along. And of course, I do expect you to take your own notes. But I will provide these notes for your reference in case I was moving too quickly and you couldn't copy everything down, like all this stuff right here. Until then, I will see you guys next time. So stay safe and bye.